Thank you, Chair. So first of all, I would want to thank the speakers for giving, the organizers for giving me the opportunity to talk here today. So I'm presenting the work I'm doing for my PhD under the supervision of Professor Mimura and partly in collaboration with Mr. Toma from Momoyama Gakuin University. So I'm talking about two-dimensional traveling waves in a free-species competition-diffusion system, and I start by reminding you of an example we saw yesterday in the presentation from Professor Taniguchi. This is a simple pyramidal front in R2, and it appears for equations like Allen-Kahn or systems like the two-species competition-diffusion system. So since for these systems we only have one kind of traveling wave, this kind of front is symmetric with respect to the bisector. And in particular also its speed must be directed along the bisector. The characteristic angle of this kind of wedge-shaped solution, which we will call eta, is can assume any value between 0 and pi. And the speed of the velocity, as we also saw yesterday, is given by this formula. So a convenient way to interpret this phenomenon is to view this kind of solution as the interaction of two planar fronts. So as I said, for example, the two-species competition-diffusion system on which we'll focus admits only one stable planarly stable solution. And when we consider the interaction of such solution in one dimension, we observe that they will collide and annihilate. And so, in the end, no structure will be left. This will obviously also happen in two dimensions if we consider planar fronts which are parallel. But if instead non-parallel interaction of planar fronts is considered, we get something more interesting. In particular, since the interaction will happen only at one point at a time instead that along all the interface at the same instant, we will have that we get some structure in the end, not only a stable state as in the 1D case. In particular, we will have two fronts moving with their one-dimensional speed, and the global pattern will move with a global speed c, which will be directed along the bisector, as I said earlier, and this whole pattern will not change shape as it moves. So we ask ourselves if there are other kind of similar traveling waves which are two-dimensional in nature. And since we are going to look for traveling waves of this kind which are originating from the interaction of planar fronts, we are going to need more traveling waves and or more different types of interaction between these kind of waves. So we will thus look into this free-species competition-diffusion system, which is a simple extension of the two-species competition-diffusion system in which those kind of solutions already have been proven to exist. So we just add a third species, which from a biological point of view will usually be considered as an invader to an ecosystem previously occupied by two other species. And then we will fix these parameters here and take the reaction rate, the growth rate of the first species as a free parameter. In a way, this free parameter represents the strength of the third species when compared to the other two. So this system is a bistable system, and the two stable equilibrium are the equilibrium corresponding to the carrying capacity of the first species and the carrying capacity of the second species. And we want to look for traveling waves connecting these two equilibria. It can be shown, well, in some cases for some parameters also analytically, but in our case numerically, that there are two different planarly stable traveling waves. So the global structure as the parameter R3 varies is as shown in this diagram, and we have a stable trivial traveling wave where W is absent, and this is exactly the same wave that appears in the symmetric wedge-shaped traveling wave. And then we also have a new traveling wave in which W is present, which moves in the opposite direction with respect to the trivial wave. And as the parameter R3 varies, also the speed of this non-trivial wave varies. There's also this arrow should point to up. There's also an unstable wave with W non-zero, but we are not interested because of its instability, and thus its difficulty to treat numerically. Okay, so we will choose one value of R3, in particular 28.3, and consider what happens for the interaction of the two different traveling waves. So we have that these two waves collide and interact destructively. And so in the same way as before, we may expect the appearance in 2 dimensions of a wedge-shaped traveling wave. However, in this case, we no longer have symmetry because the two sides of this wedge are made up by 2 different waves, which collide at the tip of the wedge and are annihilated in this point. For these reasons, also the speed and the velocity of the wave will not be directed along the bisector, but instead will happen with a certain angle gamma with respect to it. And we can compute easily this speed by observing that its component with respect to each side of the wedge should be equal to the speed of the one-dimensional traveling wave associated to that wedge, which is essentially the same formula we also saw yesterday, but in yesterday both sides had the same speed, but in this case the two sides have different speeds, so the velocity will be directed outwards the wave. So this is our conjecture at this point about what should happen in 2 dimensions. So in order to check this, we will do some numerical simulations of the time evolution problem, starting from initial conditions of this kind. These, I call them wedge-like initial conditions because they are a rough approximation of what we want to find. And so we hope that they will evolve in our wedge-shaped traveling wave. So in the left side we put a planar front, a non-trivial planar front, which forms an angle of eta with the bisector, and in the other side of the plane we put a trivial front in the same way. So obviously in this neighborhood it won't be continuous, but we can smooth it out and hope that in the time evolution problem we will reach the right traveling wave. So what happens for small values of the eta is that we actually observe what we want, which means we have convergence to a wedge-shaped traveling wave, which is asymmetric, has angle eta, and moves with the velocity we expect. So these are actually not solution of the time evolution problem, but solutions of the traveling wave equation in 2 dimensions, which are reported for the 3 components of the system. So we have on the left side the presence of W, which denotes the non-trivial traveling wave. However, if we go for larger values of eta over a certain threshold, which we call the critical angle eta c, we observe that there is no convergence. So what we see is that at the beginning the tip changes rapidly, but after a certain time it will settle and will keep the same shape and move with a constant speed. So in this case the reference frame is fixed with the speed of the hypothetical traveling wave with angle eta. So we observe that the tip moves downwards, so it means that the actual angle at the tip is less than eta. In particularly, we can observe by doing many simulations that this angle is independent on the initial angle eta and is equal to the critical angle. So our conjecture is that given enough time, when eta is greater than eta c, we will have convergence to a traveling wave with angle eta c. So why there is a critical angle in this case? If as I told you before, in the case of a symmetric wedge-shaped traveling wave, there is no limit on eta, except for being less than pi. In this case, instead, we have a more stringent Lie threshold under which existence happens. So in order to explain this phenomenon, we will think of the two sides of the wedge approximated by two rays moving independently. So this is the initial wedge position, and so we will think of this side moving independently with its speed, and the other side moving independently with its other speed. And where these two sides will meet, they will annihilate, which is denoted by these dashed lines. So when we have oriented the right side vertically in order to simplify things, and we see that when the horizontal component of the velocity of the left side is greater than the speed of the right side, these two fronts will collide, and so they will annihilate and originate a traveling wave with angle eta. And this threshold is given by this formula here. If instead the angle is greater than this, the horizontal component of the velocity of the left front will be less than the speed of the right front. So the two tips, the tip of the wedge will separate in two tips because the rays will not collide. And so this may be an explanation why when eta is greater than eta c, we don't observe the convergence to a traveling wave. So maybe a simplified setting in which we also can observe this critical angle and wedge-shaped traveling wave is the interaction of a radial front which is faster than the planar front, as expressed here. So here we have a non-trivial wave which is for R3 equal 28.3 faster than the trivial wave, and so this wave will catch up with this and interact. So if we again think of the fronts as independently propagating, we see that the angle between the two fronts will have to tend to the critical angle, again because the horizontal component of the speed of the radial front will have to equilibrate the horizontal component of the speed of the planar front. And so what we expect in this case is that after collision there will be two points of interaction which will move with the speed associated to the critical angled wave up and down, and near that point we will observe some wedge-shaped patterns. So this is actually what happens by doing numerical simulations. So after collision happens, we observe that the angle will gradually increase until it reaches the critical angle, and after the critical angle is reached, balance will occur between the speeds, and there will be no more growth of the angle, and the speed will become constant. So we will now try to change the value of R3 and see if something different happens. So for example, for R3 27.5, we have that the trivial wave is faster than the non-trivial one, and when they collide, instead of annihilation, they merge in a single homoclinic front. This has also been observed in other systems and usually happens when the speed difference between the waves is small. And the speed of the resulting front is usually the speed of the slower of the two waves. So what should happen when we go in 2 dimensions? So we have the interaction with a certain angle eta of 2 fronts, and we expect that the same will happen as in 1 dimension, which means that they will merge in a single front. Generally, this front can appear at a certain angle beta, depending on the speed of the homoclinic front. But in this case, since the speed of the homoclinic front is equal to the speed of CUV, we will have that beta is equal to 0, or so we expect. Again, also in this case, this angle beta can be computed by the same rule of speeds I talked about before. So when we again examine the interaction of the radial and the planar front, we observe that the 2 waves merge and that the angle will tend to the critical one. And possibly this pattern will become a traveling wave which moves with constant speed and constant shape. So this is, in order to be more precise from a numerical point of view, we also solve the traveling wave equation in 2 dimensions for an angle smaller than the critical one, showing that indeed we should have such solutions. So here we have the trivial front, on the right the non-trivial front, which on the lower part becomes a homoclinic front. So we change again the value of the parameters, and in this case we observe reflection of the fronts. And this usually happens when the speed difference is large. And when we go to 2 dimensions, we would naively expect that the 2 fronts will collide at a certain point and then be reflected, generating 2 fronts which are moving in opposite directions. We will call this a B wedge-shaped traveling wave. Again, the angle beta can be computed by the same formulas. However, this is not exactly what happens. I will show you this. And at the beginning there is reflection, but after a while the fronts reverse direction again, and it seems that another homoclinic front is generated. But also in this case, the interaction point and the shape around the interaction point seems to be constant. So there may be a traveling wave also in this case. So we try and solve the traveling wave equation, and it seems that there should be a traveling wave also in this case. Here we can see some kind of oscillations which are associated to that imperfect reflection which happens between the fronts, but which should decay asymptotically. So, well, I'll skip this, but it's interesting to notice that the homoclinic front should be unstable, so the stability of that wave is a bit dubious. However, if we reduce the angle of the interaction, the angle of interaction eta between the 2 top fronts, we can actually observe reflection. So we have that on the right the non-trivial front interacts with, on the left, with a trivial front, and then 2 non-trivial fronts moving in the opposite directions are generated. So we think that this behavior is essentially the same as in one dimension. So as I told you, in one dimension, the speed difference regulates the type of interaction. So small speed differences means merging, and large speed differences means reflection. And this speed can be only controlled by changing R free. However, in two dimensions, we can also control the angle eta. And for bigger values of eta, the actual speed between the fronts is reduced because of geometrical reasons. And so, if the angle eta is sufficiently large, we may have homoclinic merging in two dimensions, even if in one dimension reflection occurs. However, if the angle is small enough, we should always observe reflection, because when we consider two planar fronts parallelly interacting, we should observe the same behavior as in one dimension. So finally, as for some concluding remarks, I noticed that everything I show you today has, at the moment, no formal proof. They are just results of numerical simulations. And one problem for looking into these proofs is that we don't have comparison principle for the free species competition-diffusion systems. So the proofs shown up to now cannot be easily extended, I suspect. Another problem left unsolved is stability of these waves, especially in the case when one of the fronts is actually unstable, planarly unstable. And finally, we are also looking into the possibility to observe similar phenomena in simpler systems, for example, two-component systems, which depends on the availability of waves in such a simpler system, which we are now currently looking into. And if someone has suggestions about that, I would gladly welcome them. So, thank you for your attention.